In this video, we'll be going over binary tree paths. So given the root of a binary tree, return all root to leaf paths in any order. So a leaf is a node with no children. So in this example, we're given this tree, and then we find all of the paths from root to leaf. The first path we can get is 1, 2, and 5. So we get 1, 2, and 5, and 1 and 3. So we get 1 and 3. And then we return the list of all of the paths. Let's go over the dot process. So we will be implementing a recursive backtracking approach. So for each of the node x, we will add the value of x to our current path. Then we can recursively traverse to the left and right subtrees of x. Now, how can we determine if we have found the end of a path? Since the paths are from root to leaf, we have found the end of a path if the current node is a leaf node. And the current node is a leaf node if both of the children are null. Now, after we have visited the node x, we will need to backtrack our steps. Now, how can we backtrack our steps? We can backtrack our steps by removing the value x from our current path. This will give space for another path. Now let's go over the pseudocode. So we're going to create a list, paths, to keep track of all paths. Then we're going to implement a recursive backtracking approach. Now what parameters do we need? We first need node, the current node we are visiting. And we're going to have a path. It's going to be a string builder keeping track of the current path. And then we also have paths, list of all paths. Now, what's the base case? If the current node is null, so this is not a valid path, so we can just return from the recursive call. Then each of the recursive call, we're going to append. Before we append the current node, we're going to save the current length of path. This will allow us to backtrack our steps later, because later we want to remove the current node value. And since it's a string, we want to keep track of the length of the current path, and then we can just set the path to the original length. This will essentially backtrack our steps and remove the current node value. So we want to append node.val to path. Then if both of the children of node is null, this means we are currently at a leaf node and we have found the end of a valid path. So I want to add a string representation of path to paths. Now we want to recursively traverse to the left subtree. Then we're going to recursively left subtree. Then we're going to recursively traverse to the right subtree, basically finding the paths on the left and the right subtree. Now we want to backtrack our steps. Basically, before we recurse to the left and right subtree, we have to append the arrow, because as we can see here, after we append the current node value, before we traverse to the left and right subtrees, we want to append the arrow inside our path. So we want to append arrow to path. Then we can recursively traverse to the left and right subtrees. Now we want to backtrack our steps, which means removing the arrow and also removing the current value, right? And we have already saved the length here. So we're going to set path set the length of path or path to length. Basically, the original length of the path. This will essentially remove the arrow and the current node value. Then we can return paths after we have finished our recursive backtracking approach. Now let's go over the time and space complexity. For the time complexity, we get O of n, where n is the number of nodes. We visit each node once, and our space complexity, we get O of p plus O of h, which is equal to O of p, where p is the total number of paths, and h is the height of the tree. We get O of p is the paths list, and O of h is the recursive call stack memory. Now let's go over the code. So we're going to create a list paths to keep track of all the paths. Then we're going to implement our recursive backtracking approach to find all of the paths, the current node we are visiting, the current path, and also paths. Then we can return paths after we have found all of the paths inside our recursive backtracking approach. Then we're going to create our method to implement our recursive call. Let's go over the base case. If the current node is null, we have found an invalid path, we just return from the recursive call. Now, before we append the current node value and the arrows, we want to save the length of the current path. This will allow us to backtrack our steps later. So I want to save the length. Then I want to append the current node value. Now, if the current node is a leaf node, so if node.left is equal to null and node.right is equal to null, this means we have found a valid path. We can append or add the current path to our resulting list. Now we want to add the arrow to our path. So path.append arrow. Then we'll recursively traverse to the left and right subtrees. We'll first find all of the paths on the left subtree. Then we'll find all of the paths on the right subtree. Now, after we have processed the current node, we want to backtrack our steps by removing the arrow and removing the current node value to give space to another node to find another path. So on a path, set length to the original length. This will essentially remove the arrows and remove the node value. Let me know if any questions in the comment section below.